All right, here we go. So this is reaction video number 34, I think. Today is a really cool one. So on Twitter, a couple of people have been paying attention to these daily postings that I have, and this person said, "Hey, could you please do one of mine?" I was like, "Sure, let's do it." So usual, I don't know where to put my face. Here we go.
Yay!
Yay! One more interesting thing you might find in kinematics is a two-dimensional collision. Now, sometimes what we mean by collisions is that we'll conserve momentum, but that's for a later unit.
Okay, wonderful green screen. Notice how well it's doing around his head. Even in here, it's nailing it. This is much better, it seems to me, than the on-the-fly stuff that Zoom and Google Meet do. So sometimes these are pretty distracting, but this one is really done well. So I wonder if Tad has a green screen behind him. Maybe I'll ask him. Let's see. The reflection of his glasses is showing us his screen. I can't quite make it out. I love the beginning too. Hey, let's get excited. Why not? Let's do it. Here we go.
But maybe what we want to know is, will two objects collide or maybe intercept? So maybe I've got this object V, right? And V, I think I put V over here at, let's see. Oh yeah, -4, 3. Those are its coordinates. And it's traveling at 2 in the X and -1 in the Y, right? 2.
So there's so many different ways that you can write vectors, and this sort of bracket vertical notation, it really keeps it separate. I think it really helps you see the connection between the X's and the Y's because they're kind of on the same horizontal level. Compare that with like a -4, 3, or as Rhett Elaine always does, which is VPython notation. So bracket X, Y, Z bracket. And if you had two of those next to each other, they might be harder to tell the interesting comparisons. This is a really interesting point. Like, let's find out if they're going to collide at all, and then figure out what might happen with it. That's pretty cool. Let's see. I liked, so we shifted from the, whatever it was, green screen to this blackboard, or whatever you call it. Lots of useful color, decent handwriting. I have to say that I just noticed this isn't perfectly centered, so I'm going to say it's spinning. I'm guessing it's probably not. I also think it's really interesting, these choices of the letters, right? So R and V we're totally used to, and then, there's a whole other one. Let's choose two completely different letters. So I'd love to hear from people in the comments comparing and contrasting this with subscripts. So R sub 1, V sub 1, R sub 2, V sub 2, versus let's just use completely different subscripts. Or, right, the idea that he could really just stick with colors. Now, that's another really interesting way to think about this, is what if you just totally stick with colors? And then, of course, white, I guess, is just for general definitions, though already there is a slight sort of repetitive use of the letter V here. So let's just keep an eye on how that goes.
2I minus J. And then I'm sitting down here, maybe I'm the red object. I'm sitting down here at X equal 1, Y equals -4. That's my position.
Oh, I'm blocking his face.
I want to intercept it, right? I want to fire some projectile that'll intercept it.
There we go. Sorry
so
about that.
What I want to know is, what is that vector for the projectile? How am I going to intercept V if I'm sitting down there at S? All right.
This is a really cool problem.
What this really is a two-dimensional collision. I want to find out at some time where am I going to collide with this thing? Okay, so we're free to choose, because I can choose any time I want, really, as long as, maybe if that's, an asteroid headed for the planet or something. I mean, there's some sort of deadline beyond which, I'm going to make sure I intercept the thing. But anywhere along that path, I could choose to intercept it. So I'm going to choose.
Okay, so this is really, really fascinating. I'm really fascinated by being able to write where you're looking. And so when I first got a pen tablet, I had to really train myself to be able to write while looking at the screen. And it felt a little bit weird because I was used to looking at my fingers. And you can actually get used to that pretty quick. Usually what I tell people, if you buy like a Wacom bamboo tablet or something, literally just write the alphabet like 3 times and you're good to go while looking at the screen as opposed to looking down at your hands. But notice what he's doing, right? So he's looking down, and definitely whatever he's writing on is digitally also right here. And before, when I was looking at his eyes, he was kind of looking, I guess, to his right. And so I think he just has 2 screens going on here, because he wasn't looking down. It's not like he has his screen down below with a camera up here somewhere. I think he has 2 screens because he's looking down, writing, and it's showing up above. So these are all the sorts of things to think about for you if you're contemplating ways to sort of up your hardware game on how to do this. So we don't see his eyes and he's talking, we're still hearing him fine. So compare and contrasting that to him looking up while writing, what is the best thing for you when doing this?
I'm going to choose 4 seconds. So how am I going to intercept this thing in 4 seconds?
Cool.
What I'm going to use is...
So I'm sorry to pause, but I'm not sorry to pause. I pause all the time. Why did I even say that? I'm not sorry to pause. I was originally thinking that this arrow meant something, right? That this angle, almost like 45 degrees to the up and to the right, meant something. And so I was like, what is he talking about? There's only one possible time when these 2 lines interact. You can't just choose it. But now I realize that W is a question mark, and it's actually stated in both places. So this actually could be any old place. And he's like, I think what he's going to do is figure out where this is in 4 seconds and then make sure the sucker gets there at that point, which, he's guaranteed to be able to find a solution, as opposed to if you just arbitrarily set this, they're most of the time they're going to miss each other, even though technically this line and this line cross. They might not cross. They might not be there at the same time. So he's kind of inverting it a little bit. And I was thrown off at first because he just drew this and I just assumed this was the answer. Now, it's possible that he worked this problem before, and it turns out that this all works out perfectly to be roughly at 45 degrees like this. But I'm guessing this was just a random, hey, who knows which way it's going.
Is this up here, I'm going to use our definition of V. But notice we're in 2D now. These are vectors. So before, we've always done motion in one line, just X and Y. So
just watch his eyes again, right? So he looks down, he looks to his right to look at the screen, and then he looks at us. And that's something I don't do very often. Really being aware of all of that, I think, is super, super cool. I'd love to know from Tad if he watches himself. Because, for me, I'll be honest, sometimes I'm just drawn to my own face. So I'm just making sure I look okay. And so I've noticed that in Zoom and in Google Meets, you can kind of hide yourself. In Zoom, you can completely hide yourself. In Google Meets, you can minimize yourself and basically not focus so much on yourself. And I was talking to some students. A lot of them say, yeah, I just look at myself, make sure I look okay. And so I really like what Tad's doing here, because he has he understands who we are, the camera. He understands that he needs to look up. I'm guessing he could look down also, but I think it's better for him to look up at his screen.
Let's use V is now, the definition is that it's delta R over delta T, where R is the vector, X and Y, right? So let's write this down in a little bit better form. This means that my delta R is V delta T, right? So that means my R final minus R initial is V delta T.
Mm-hmm.
Or here's the useful way that we'll write it. R final, my final position is just my initial position plus V delta T. Right?
So pausing only to say something about reaction videos. So you guys have probably gotten frustrated with me never knowing where to put my face. And whatever, I don't mind being flexible. I'll just move it around. But it's really interesting to compare and contrast reaction videos to some music video or some cool sports thing I watch a ton of reaction videos. I just love them. If I find a song that I really like, I love watching reaction videos so that I can hear experts saying why it's so cool, right? But anyways, they tend not to have to move their face. They often usually do a little bit better of green screening, but no matter what, at least their face is blocking the some of the video. But in a physics video, man, we are using every single square centimeter of the screen with our writing and our drawing. So that's why I need to get out of the way. I could, of course, like shrink their video and put my stuff on the outside, but I like their stuff to be as large a font as possible. So anyways, I just think that's interesting.
All right. I'm sort of just updating my position from
Yes,
where
perfect.
I was, our initial, to where I'm going to be, because every second I'm moving along that velocity vector. After 1 second, I'm here, right? And after the next second, moving along that vector, now I'm here, and then I'm here.
Oh, I like that.
So on. Okay.
I like that.
So, what does it mean for one thing to intercept another? What it means is
Look at that. Look what 4 seconds did. 1, 2, 3, 4. This was right. This is about right. Because in 4 seconds, this thing is going to be here. Now, we didn't know that this is how far it was going to travel in 1 second. Let's see. He did -4, 3. So it moved over 2, down 1. Actually, this is basically drawn to scale. So it turns out that this orange arrow is pretty dang good at guessing where the answer is going to be. So that's really interesting.
Is that they're both in the same place. So here's our condition. This is what we're going to do. What we're going to say is that R final for the blue object is going to be the same as the R final for the red object, right? When one intercepts the other.
Love it.
They're both at the same position. So I'm going to set those things equal to each other. So here's what I'm going to do. What is my R initial for the blue object? It is -4 and 3. And then my V delta T, my V is 2 - 1. And then I've chosen 4 seconds. I'm going to intercept this thing after 4 seconds. All right, that's going to be its final position, right? Maybe it's...
So just a commentary on the way he orients his symbols, right? So he's really centering these things well vertically. So the plus is centered vertically, the multiplier is centered vertically, and then so is the scalar. So students, I'm sure in his class already know, okay, this thing together is really 8 -4, right? You can multiply this 4 here and multiply this 4 here. There, actually, I think there's benefits to the Rhett Elaine Python way or the parentheses with commas, because students are used to scalars outside of commas distributing through. I think scalars distributing into interesting brackets like this is probably a new thing, but I'm sure this is not the first time they've seen it this way in Tad's class. But it's just interesting to think about, right? Like, is that obvious? Is it something you need to tell them? Could it possibly be some other interesting meaning?
Maybe it's right there or whatever.
Or whatever. He knew where it was going to be.
Position for the red thing then too, right? The thing that I launched. So this is going to be equal to, what is the initial position for the red thing? I said it was 1 and -4 plus. Now, here's what I don't know. I don't know the velocity vector, right? I need to know what the vector is along which I launch this thing in order that I intercept the blue thing. All right, so I don't know what it is, so I'm just going to call it W. That's what I'm after. Times the same amount of time, 4 seconds.
So that's really interesting. So when you look at this, it's really 2 equations. Let's be honest. It's an x equation and it's a y equation, right? And there's 2 unknowns, the x component of W and the y component of W. So I was actually expecting right here that he was going to do a bracket and then do like W sub x and W sub y. But he wants to think of it as a single thing. So this looks funny right now, right? It's like, well, hang on a second. I got brackets, 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 then no brackets. And so I think that the scaffolding that he has done with his students to think, look, sometimes we're going to call it a thing, W. Sometimes we're going to bust it up into 1 or maybe 2, to 2 or maybe 3 elements. I think that's really, really interesting because basically this is going to turn into two completely separately solvable equations. The x equation is going to be easy. The y equation is going to be easy. Interestingly, it's, oh my God, two equations, two unknowns. Do I have to do some matrix stuff? Nope. These things are going to be absolutely straightforward, right? He can separately do the x, separately do the y, because this is truly two different things going on. This thing is moving in the x direction. And this wants to get to the same x location at the same time, and it's moving in the y direction, and it wants to get to the same y point at the same time. It's really two different things, just sort of combined as a single statement. And so I think that's really interesting. I'm just going to back up just a little bit so we don't miss it.
That's what I'm after. Times the same amount of time, 4 seconds. Right, there I go. Okay, so what I'm going to do, this is just a vector equation. No problem, we can manipulate vectors. So I'm just going to manipulate these vectors as their own little objects, and I'm going to solve for W. All right,
cool.
So we know how
cool.
to do this.
That's different than what I said.
-4 and 3 plus, I just multiply a vector times a scalar there. I'm just going to multiply each component times the thing. So that's just going to be 8 and -4. This is equal to 1 and -4 plus 4W. Okay, neat.
Cool.
All right, so on the left-hand side, I'm just going to add those vectors together, just like it says. So let's bring it over here. So on the left-hand side, I've got, what, -4 plus 8. That's going to be 4. 3 plus a -4, -1. Is going to be equal to, apparently that's where...
You know what? I just stopped to comment on the very same thing he was about to comment on. I'll just say my piece quickly. I think a lot of students will say, "Oh my God, I'm going to bring this over right away. I'm going to bring this term here over to the left-hand side because I need to get all of the stuff I know on one side and the stuff I don't know on the other side." But I was noticing that by leaving this side alone, this is literally where they're going to cross. 1, 2, 3, 4, down 1, right? This is a very physically meaningful thing. So if you had brought this over to the left side early, you wouldn't have had this moment where you knew what this was. And I'm pretty sure he was just about to say that. I'm going to back him up and let him say it.
1 is going to be equal to, apparently that's where these things are going to collide.
Yes, perfect.
This is 1 -4 plus 4W. Okay, now I just subtract that vector from the right-hand side to the left-hand side. So what do I get? 4 minus 1, that's going to be 3. 1 minus a -4, looks like that's also going to be 3, right? Plus 4W. So I'm just doing vector algebra. So now I divide both sides by 4. So that means I divide both components by 4.
It was 45 degrees. Look at that. It was 45 degrees.
It's just going to be...
How do I know that? How do I know this is 45 degrees? Because these two things are the same. After he divides by 4, they're still going to be same. So it really was 45 degrees.
What, 3/4 and 3/4, right? So that's 0.75, 0.75 meters per second. There we go.
So I just want to pause quickly. There's a lot of people who would really rather write that as 3/4, like a fraction. But fractions inside brackets get hard to read. So writing it as 0.75, nice and compact, right, and is the whole story. Very, very interesting. I really like the approaches that he's taking to this. You know, back here, I said this was 2 equations, 2 unknowns. Let's just do each one separately. That would have totally worked. You would have said, if you had called this like an x and a y, you could have done x, you could have done y, and each of them would have separately yielded 0.75. But by doing it together, first of all, he has this awesome result. This is literally where they're going to smash into each other. And then it really feels like he's just doing one solution. I think that's really cool. I'm going to back him up a little bit, let him conclude.
0.75 meters per second. There we go. So if I launch something, there's my vector. If I launch something at 0.75 and 0.75 in the x, 0.75 in the y, then after 4 seconds, I will intercept that blue thing. Bang. That's what this is really telling me. Okay, very cool. Um,
All right, I think I'm just going to stop there because I just want to say a couple more concluding things here. So, the fact that it was 45 degrees from the horizontal is not enough, right? You also have a very particular speed you need to go. It's not 0.75; it's actually, the magnitude of whatever this ends up being. So, this is a really cool problem. I'm really intrigued by what you guys think about the fact that when he drew it, he happened to draw it right. So that's a really interesting question. He said, well, I don't know what this is. He could have not drawn this. He could have drawn it this way, which of course isn't right. He could have drawn it this way, which of course isn't right. I think that when he made this choice, it was tied to this. So I'm just going to guess that he had already worked the problem or maybe seen the solution or something, because it was just remarkable how well everything kind of came together here. But I guess my question is, if a student were to do this problem, they might not get that lucky. And so they might wonder, boy, why did it seem so much cleaner when my instructor did it? So I'm just fascinated by the idea of being ready to make these videos, right? Practice, understand, read ahead, all of that stuff. But then maybe hinting at the answer at the beginning. And how does that help our students learn? I think that it made it so that this drawing was super, super useful. Right? It totally drove home the points about what was happening. But on the other hand, it made it seem as though this wasn't as unknown as we thought. So I just found that really, really interesting. So the things I loved in this video, I loved the green screen. My God, his green screen works really well. I'd love to know what software he's using. I love this approach to the vector notation. I think that being able to see across the X's and the Y's was super, super cool. And this idea of solving this all together and pausing here so that this was a physically meaningful event, super cool. All right, everybody, thanks so much. Have a great day. And remember, physics teachers are awesome.